what I wanted to do is go back to where we started talking about just dry gas. And in the reservoir rate equation here, talk about what happens to this figure here, the gas mobility. Okay? So what happens to that for gas condensate? So I'm going to make in red. So if we've got gas condensate, so let's just say that as in the COOF that we've been looking at, let's say just by chance this initial reservoir pressure here is approximately equal to the dew point. Okay? Or this, let's just say that this is where we have, this is the dew point pressure of a gas condensate. So what's going to happen is that out here, this is what? This is region 3, and nothing changes. Okay, so if our initial reservoir pressure is out here, our dew point is here, then nothing changes. The area under the curve is still what you want to use to drive the gas between PRI and P dew point. Nothing changes at all. You can use the same pseudo pressure function. But now we basically have flowing bottom hole pressure way below the dew point here. So what's going to happen is that this region 2, it's going to have a KRG effect. So now in the gas condensate, this is now equal to 1 over mu GBG and times KRG, or KRG P over mu G ZG, something like that. Okay, it's going to be one of these two. And so what's going to happen below the dew point in region 2, there's not that much condensate buildup, so the KRG is going to go down, but it's below the critical saturation. So it's going to drop down some, but not very much. So I'm going to just draw it like this. And then we reach that 47 barrels per million. And we leave region 2. Okay, so this is our region 2 behavior. And you see there's not much area loss, right? But when you get to region 1, this guy's going to go down, drop like a rock. Something like that. Now this is region 1, at least at this particular time, because this here is P star. Okay? And now the area under the curve is this area here. Drops slightly here, and then follows this line here. Okay? So that's the area under the curve. So the amount of gas rate that you've lost is this, how are you going to make, what color want to make that? Pink. This amount of gas rate that we've lost is this proportional to this area here relative to the total red area, or actually the area of a dry gas. So you've lost that much compared to dry gas. Well, so the one thing is that that loss of area is not a factor of 2, is it? Like I told you about. I said, the productivity loss is about a factor of 2, a rule of thumb. But that's if the initial reservoir, if the current reservoir pressure is near the dew point. Okay, if you get rid of this to the right over here, the undersaturated part, what you see is that, in fact, you've lost about half the area to the left of this. So as the reservoir pressure drops from that initial, when the reservoir pressure reaches this point here, then the rate compared to a dry gas well at that same average pressure, it's going to be about half. The higher the degree of undersaturation you have, the less effect you have of the condensate blockage, because that area is a small part of the big area. As the reservoir becomes more and more near saturated, that blockage effect becomes more and more important. And the most important field to ever have shown condensate blockage as a serious problem was the Arun field, I think in either Indonesia or Philippines. I think it's Indonesia. I should know that.
I think you mentioned Indonesia.
Yeah. So the Arun field that was operated by Mobil, they had a gas condensate, not very high liquid yield, very high temperatures. So the maximum liquid dropout was about 2%. They thought, oh, this is not going to be a problem. It had, I think, 2,500 pounds under saturation. So they drilled their 160 wells that was going to deliver gas to Asia for the next 15 years. And what happened is as the reservoir pressure dropped and they needed to have bigger drawdowns to make the rates, all of a sudden when they drew it down, they didn't get the total area that you see in blue there. And so after about 8 years of producing the field, they found out, oh shit, we've got to drill another 100 wells to make up for this problem. So it was a big deal.
The loss in productivity is because of the relative permeability, right?
That's right. Region 1 KRG drop. That can be from 0.05, the KRG, to 0.2.
Is there any other factor like the total energy is now shared between the liquid and gas phase? Is that a contributing factor?
I didn't quite catch the question.
The total energy of system will remain same, and now you have liquid and gas instead of just gas. So the gas energy, the molecule energy of the gas will go down. So will that be a contributing factor?
No, I'm not sure what the energy you're talking about means, but no. This is what we're going to talk about the next 2 days.
Right.
But basically what happens is that you get this region 1 two-phase steady state flow. What enters has to leave very quickly. And when you get that steady state flow, you need a substantial oil saturation to give the mobility to carry all of that liquid out together with the gas, so there's no accumulation. And it's like pipe flow. What enters the pipe leaves the pipe, and it just rearranges it however it must. It rearranges itself to accommodate that. So here you get a saturation mobility profile that accommodates making sure that whatever enters region 1 leaves region 1. And to get that mobility profile, the KRG ends up dropping substantially in region 1.
Thanks.
So that's this changing the area. It's a little bit complicated thing to do, but we can do it in a first order way. we can say that in region 1, the KRG is just a number. It's constant. It's not too far from being constant. Okay? And that magnitude is 0.2 or 0.05. If it's 0.05, then that area really drops off. Okay? And then it depends, do we have any undersaturated area to dry the gas? If it's near saturated, you don't. So you start losing a lot more. So it may be the skin effective condensate blockage skin may be something like 20, 30 instead of 5 or 10. So equivalent skin effect. So
does it have anything to do with the richness of the gas condensate?
That's right. So if it goes to 0.2, it might be a lean gas. In fact, the Arun field didn't have a KRG that went to 0.05, it went to 0.2, but it was enough to lose, I think they said they lost 60% of the area, 40% of the area, if I remember right. So, yeah, they lost 40% of the area.
But the gas in the pink region is not a loss in terms of recovery, but it's just delaying the gas production more or less severe, isn't it?
It's not anything to do at all with recovery of condensate. Nothing. Third decimal. But it's related not to a delay, but it's just related to the fact that you need larger drawdown to produce the same rate, or you just simply don't get as much rate for the same drawdown.
Yeah. So productivity.
Productivity is what you lose. Yeah, exactly. Productivity loss. Yeah.
And did they manage to solve this compensate that issue? Was there any remedy?
What was that? In the Arun?
Yeah.
I don't know the details of the field. I suspect that there was plenty of new wells and probably some stimulation of existing wells, I'm guessing. I don't really know the but that was the so I don't know exactly what combination of well enhancement it was to new wells, but it was definitely a lot of unexpected costs. So, and what they did is that they ran full field models with not treating any of the condensate at all. They just thought, well, it's such a lean condensate that, and all this understanding of, was not there. They just ignored it basically in their modeling. So in the original design of the field, they didn't, I don't know the details, but the reference is given, and in I'll probably use some of the e-notes tomorrow and Thursday. The reference to that and the discussion of that is included there. But this is just the picture you need to take away with you of what's actually happening with the condensate blockage. In terms of adjusting the gas rate equation, that's what happens. And in the tubing, I can't say too much here other than for gas condensate here, you definitely are going to have S will be larger, okay, just simply because the molecular weight of the well stream is higher than a dry gas. And there'll be some two-phase flow effects here. So there's going to be some kind of a CGR producing oil gas ratio effect in this effective term here. But it may not even be enough to be correlated. So like what we did in this North Sea field that we just recently worked on, we found the CT and S that gave a very good fit of all the Prosper generated. I think it was, which correlation do you remember? Gray or anyway, and this was a very high pressure gas condensate, so it was rich high pressure gas condensate. So we got the pressure drop in tubing correlated with this equation pretty much for the whole life of the wells of the field.
I didn't remember the correlation. We got the tubing table.
Yeah, so it was not a big variation in fact I think we used a single, we just adjusted the CT and the S to match the
So you define a wider range of CGRs, right?
yeah, well, in the Prosper tables, it takes into account the CGR, but what we did is we just took the flowing tubing pressures and flowing bottom hole pressures from the model over the whole life of the field, right? And then correlated it with this equation.
Yeah.
So it built into it and gave pressure drops that were very reasonable for the whole life cycle of the field. Of course, if you change the well configuration, you have to rerun the Prosper, you have to refine the value of CT and S. But.
Yeah.
At least for first order effect, you can do something like this, I think.
Sorry, am I understood correctly? The S in the equation is the skin factor that you just referred to?
No, so this S is in this paper by Fetkovich. It's not, he didn't derive it, but it's gas tubing. Actually, this is the paper, this is the thesis I mentioned about, let's see, Fetkovich, yeah, there it is. This Fetkovich gas deliverability paper. It's a standard gravity term. You can derive it analytically. Oh, goodness. It's up here somewhere. There it is. S is equal to G is the gas gravity, H is the true vertical depth, and the temperature average and Z average. So it's a very, very simple term. And here it even says, this S should not be confused with skin. I remember, this is Mike Fetkovich here. I remember he was reading a paper or a report, and that person had used capital S for skin. I think he went ballistic. Yeah, because this S is such an important term on the tubing side that the capital S has a very, very special meaning. Of course, it's saturation as well, but I mean, capital S by itself, without anything, that is always this, I think it's capital S here. Yeah. So it's capital S here. And yeah, the little s, skin factor. So you can see it's a very simple term. It's just a gravity term, basically, for the density. Okay. Yeah, so I think this leads us pretty well into tomorrow's discussion, which will be dedicated to the condensate blockage, as well on Thursday to some extent.